So if you remember in the last part, we derived two tests based on the maximum likelihood estimator. And we want to do these two tests on this example of the Pareto distribution. Right? And so in order to do that, we first need to, of course, calculate the maximum likelihood estimator, as well as, in the case of Wald's test, the Fisher information. Right? So this is a good exercise to actually do this. So let's find the MLE. So to find the MLE, we first need to write down the likelihood, right? The function that we want to maximize. So the likelihood of our data, given theta, right, is just going to be the product of the probabilities of each of the xi's, given theta. Right, so just the product of the individual densities of each xi. Plugging in the form of the function, it's theta xi to the minus theta minus 1. And now if I multiply this out, I get theta to the n times the product of the xi's, all raised to the minus theta minus 1. Right here I took this product, I multiplied all of these together, and since they all have the same exponent, you can of course move the exponent outside of the product. Okay, so we want to maximize this function, and normally what you do is you take derivatives and set it equal to 0. This is of course a hard function to take a derivative of, so what we normally do in situations like this is take a log, right? So the log likelihood of x1 to xn given theta is just the log of this okay? And of course you can do things with logs like break it up over products, so we would have the log of theta to the n plus the log of the product to the minus theta minus 1. And then the log of something to a power will just bring the power outside of the log. So doing those two steps at once, you'll find that this is equal to n log theta plus, right, the log of this product term, bringing down that exponent, we minus theta minus 1, times the log of this product, and the log of a product is again the sum of the logs. Okay, so this is our log likelihood function. Now let's take a derivative and set it equal to 0. So the derivative of L with respect to theta will just be n over theta. And then from here we get a minus sum of the logs. Right? And we want to set this equal to 0 and solve for theta. So if we set this equal to 0, we can add the log to this side, multiply the theta and divide by the log. Right? This is just algebra. You'll find that the stationary point of this function will be at theta equals n over the sum of the logs. Now to actually check that it's a maximizer, right, you can take another derivative and check that the function is actually concave. So the second derivative of L with respect to theta, from this term we get a minus n over theta squared. And then this term doesn't depend on theta, so it just disappears. Now theta squared is always going to be positive. N is just a positive integer, so this is of course always less than 0. Right? And this then tells us that the function is concave, and this is in fact a maximizer. So we're justified in writing theta hat MLE equals n over the sum of the logs. Now finally, we also need the Fisher information to do Wald's test. So what is the Fisher information? Remember that the Fisher information is the expectation of the minus second derivative of the log likelihood, right? So it's the expectation of the minus this. Now normally when we write the Fisher information, we want it with respect to one copy of x, right? If we take the expectation of this, that would give us the joint Fisher information of this whole sample. But when we write I of theta, we just want the expectation of the minus second derivative of the likelihood of 1x. Now, if you go back through this with just one copy of x instead of n copies, right, you would have a theta times x to the minus theta minus 1. You go through this work, and you would find the derivative of the likelihood would just be 1 over theta minus log of x. And then the second derivative will just be minus 1 over theta squared. So this is just actually equal to the expectation of minus 1 over theta squared. This doesn't depend on x, so we don't actually have to take an expectation. This is just a constant. And so the Fisher information is 1 over theta squared. Okay, so this is the Fisher information. This is the maximum likelihood estimator. We're now ready to construct our tests.